Okay, so let's unpack this idea. We've all used formulas for the area of shapes, base times height, half base times height, stuff like that.
Right.
But what if the smartest way to figure out areas sometimes isn't about plugging in numbers, but just seeing how shapes are sitting next to each other?
That's exactly what this source material gets into. It lays out these area theorems that give you some really neat shortcuts for comparing areas, especially, when shapes share a base or they're kind of sandwiched between the same parallel lines.
Okay, so our mission here for this deep dive is really to pull out those key insights from the source, those sort of simple geometric rules that give you that aha moment, making area stuff much clearer for you listening.
Right. And the source kicks off with some basic definitions we need. It talks about equal figures, simple enough, ends with equal areas.
Okay.
But here's the important bit, the distinction it makes. Congruent figures, they always have equal areas, but figures with equal areas, well, they're not always congruent.
Right. Okay, just that's super clear for everyone. Two shapes can take up the exact same amount of space, area-wise, but not actually be the identical shape. Like one could be tall and skinny, the other short and fat, but same area.
Exactly that. Perfect example. Then the source brings in this idea of figures between the same parallels.
Okay.
Think of shapes where their bottom edge, the base, is on one line, and their top points, or maybe a whole top side, just touch another line that's perfectly parallel to the first one.
And when shapes are set up like that, between parallels, what's the main geometric thing we need to know?
The absolute crucial takeaway is they automatically have the same height, the same altitude.
Got it. Same height. Makes sense. And then there's figures on the same base, or on equal bases.
That just means what it sounds like. Their bases are literally the same line segment, or maybe different segments, but with the exact same length and lying on the same line.
Okay, bases covered.
Exactly. So with those definitions down, the source gets to the really interesting stuff, the theorems. Theorem 19, it says if you have two parallelograms, right?
Yeah.
And they share the exact same base, and they're sitting between the same parallel lines, their areas have to be equal.
Wait, really? Just like that? That seems almost too simple. The source mentioned something about congruent triangles in the proof. How does that work?
Yeah, it's quite elegant, actually. The proof basically shows that the bits of the parallelograms sticking out at the ends, beyond the shared parts, are congruent triangles. They've just shifted position. So when you add back the middle section they both share, the total area stays identical.
Ah, okay. You're just moving congruent pieces around.
Precisely. And there's a neat little add-on, corollary. A parallelogram and a rectangle on the same base and between the same parallels also have equal areas.
Which makes sense, yeah, because a rectangle is just a specific kind of parallelogram, right? Just with right angles. Okay, Theorem 19 down. What's next?
Theorem 20. This one brings triangles into the mix. It states that the area of a triangle is exactly half the area of a parallelogram, provided they share the same base and are located between the same parallel lines.
Half, okay. The source hinted the proof involves sort of completing the triangle.
Yes.
Making it into a parallelogram.
Yes, exactly. You draw lines parallel to the triangle sides to form a parallelogram, and the theorem shows the original triangle is precisely half of that new shape.
Oh, good.
And this leads pretty logically to Theorem 21. Triangles that share the same base and are between the same parallel lines must have equal areas.
I think I see why. Because using Theorem 20, each of those triangles would be half the area of a parallelogram on that same base and between those parallels.
Right.
And by Theorem 19, those parallelograms would have equal areas. So the triangles, being half of equal things, must be equal too.
You've got it. That's the logic. And the source as an important note. These rules equal areas, or half area. They also work if the figures are on equal bases, not necessarily the identical base segment, as long as they're still between the same parallels.
Okay, so the length of the base can be the same even if it's shifted along the line.
Correct. And one last little point the source includes. If you happen to know two triangles have equal area and they stand on the same base, or equal bases, then their heights, their altitudes, must also be equal.
Interesting. Sort of the reverse logic. So, okay, theory's great, but how does this play out in, like, solving an actual problem? The source had a good example, right? With a parallelogram AFE.
Yes, exactly. Let's walk through it. Imagine parallelogram AFEC has an area of, say, 140 square centimeters. Now picture another parallelogram, BFED, and also a triangle, BFD, kind of connected to it visually.
Okay, got a picture. AFEC is 140.
Right. Now look at the second parallelogram, BFED, and compare it to the first one, AFEC. What do you notice about their bases and their position?
Let's see, BFED and AFE.
Yeah.
Okay, they both seem to be sitting on the line segment FE as their base.
They are.
Yeah, their top sides, AD and BC, seem to be on the same line, AD, which looks parallel to FE. So same base FE and between parallels AD and FE.
Perfect. So applying theorem 19 parallelograms on the same base between the same parallels, what can we say about their areas?
They have to be equal. So the area of BFE must also be 140 square centimeters.
Exactly. See, no need to measure anything about BFD itself, just its relationship to AFC tells us its area.
That is pretty powerful. Okay, what about the triangle BFD?
Okay, now compare triangle BFD to the parallelogram BFED. What's their relationship? Look at the base and parallels.
All right, triangle BFD, parallelogram BFED, they share the side BD, looks like that's the base for both. And they are both between, the parallel lines BD and FE.
Correct again. Same base BD between the same parallels BD and FE. So what does theorem 20 tell us?
Theorem 20 was triangle and parallelogram. The triangle's area is half the parallelogram's area.
Yep.
So area BFD would be half of area BFED, which we just found was 140. So half of 140, 70 square centimeters.
Precisely. 70 square centimeters. And again, we didn't need the actual length of BD or the height, just the shared base and parallel lines.
Wow. Okay, so just understanding these relationships, shared base, equal bases, between the same parallels, lets you figure out or compare areas in a much simpler way sometimes. It's not always about the standard formulas.
That's really the core takeaway. These theorems give you this elegant geometric lens to see how areas relate just based on how shapes are arranged.
Yeah.
It can cut through complexity really nicely.
So wrapping up the main idea from this dive, if you spot figures on the same base, or maybe equal bases, and they live between the same parallel lines, you've got predictable area connections. Equal areas for parallelograms, half area for triangles compared to related parallelograms.
That's the heart of it. And just to leave you with a little something extra to chew on, the source material also mentions another situation. Think about triangles that don't share a parallel line up top. Instead, they share the same top vertex, like a single point where they meet, and their bases are just different segments sitting along the same straight line at the bottom.
Oh, okay. Different setup.
Yeah. In that specific case, the source hints that the areas of those triangles are proportional to the length of their bases. So if one base is twice as long as the other, its area is twice as big. How might that rule pop up in different geometry puzzles you might encounter? Something to think about.